Water beyond Earth, where we found it in our solar system. There is more liquid water in our solar system than most people realize, and almost none of it is on Earth. That sounds backwards. Earth is the blue planet. 71% of its surface is ocean. But here is the thing. When you look at the moons orbiting Jupiter and Saturn, the picture changes completely. Some of those moons hold oceans larger than all of Earth's seas combined, hidden beneath shells of ice, in total darkness, warmed not by sunlight, but by the gravitational squeeze of giant planets. Water, it turns out, is not rare in space. What's rare is finding it on a surface. What's common, surprisingly, even abundantly common, is finding it buried. Let's go through the solar system, body by body, and look at where water has actually been found. The Moon. Start close to home. The Moon was considered bone dry for decades. The Apollo samples came back parched. Textbooks said so. Then, in 1994, a military spacecraft called Clementine bounced radar signals off the lunar South Pole and got back a reflection that didn't quite fit bare rock. Inconclusive. Then, in 1998, the Lunar Prospector detected hydrogen concentrated at both poles, strong enough to suggest ice, but not definitive. The real break came in 2009. A NASA spacecraft called LCROSS deliberately crashed its rocket stage into a permanently shadowed crater near the South Pole. The impact plume contained the spectral signature of water ice, clearly, unmistakably. Then, India's Chandrayaan-1 mission, with a NASA instrument aboard called the Moon Mineralogy Mapper, provided the first direct surface-level confirmation. Water ice in polar craters where sunlight has never reached, some for billions of years. In 2020, another surprise. NASA's SOFIA mission, an infrared telescope mounted in a converted Boeing 747, detected water molecules not just in shadowed polar craters, but in sunlit regions of the lunar surface. Embedded in dust grains, scattered across the face of the Moon in far more locations than anyone expected. Then, in late 2024, a fresh analysis of Lunar Reconnaissance Orbiter data showed the ice deposits extend well beyond the South Pole, reaching down to at least 77 degrees south latitude, more widespread than previously mapped. The Moon is not a water world. It is extraordinarily dry by Earth standards. But it is not dry at all by the standard of bare rock. Mars. Mars had rivers. This is not a hypothesis. It's written into the planet's surface. Valley networks, ancient lake beds, the remnants of a vast northern ocean that covered perhaps a third of the planet more than 3 billion years ago. Mars was wet. Then it lost its magnetic field. Its atmosphere thinned, temperatures dropped, and the water largely vanished. Largely, not entirely. Today, Mars carries more than 5 million cubic kilometers of water ice at and near its surface, mostly in the polar caps. Enough to cover the entire planet in a layer 35 meters deep. The Phoenix lander dug into Martian soil in 2008 and found ice just a few centimeters down. The Curiosity rover confirmed it again in 2013. But ice on the surface is the easy part. In 2018, the European Mars Express spacecraft found something more interesting. A radar reflection from beneath the southern polar ice cap, about 1.5 kilometers down, consistent with a body of liquid water roughly 20 kilometers across. Salty, almost certainly. Salt lowers the freezing point enough to keep water liquid in those conditions. Whether it is actually liquid water or something else, very cold, highly reflective brine, or certain types of clay, remains debated. Not everyone is convinced. Then, in 2024, a study using seismic data from NASA's InSight lander suggested something larger. A layer of fractured rock saturated with liquid water between about 11 and 20 kilometers below the surface. If the interpretation holds, it would represent a volume comparable to a global ocean. Deep, unreachable with any near-term technology, but there. Mars is a planet that traded its surface water for something buried. The full ledger is still being counted. Europa. If there is one place in the solar system that scientists talk about most when they mention the possibility of life beyond Earth, it is this moon of Jupiter. Europa is slightly smaller than our moon. Its surface is a shell of ice, cracked, crisscrossed with brown streaks, geologically young. Almost no craters. That lack of craters means the surface is constantly being renewed. Something beneath it is active. The first serious hints came from the Voyager probes in 1979. The surface looked broken, young, strange. When NASA's Galileo spacecraft arrived at Jupiter in the 1990s and began measuring Europa's magnetic field, it found something unexpected. The field was distorted in a way consistent with a saltwater layer beneath the ice, conducting electricity. A subsurface ocean. The ocean is thought to be between 60 and 150 kilometers deep, far deeper than any ocean on Earth. The ice shell above it is estimated at anywhere from 3 to 30 kilometers thick. Water in direct contact with a rocky seafloor. Heat from tidal flexing. Europa is squeezed and stretched as it orbits Jupiter, generating friction, generating warmth. Possibly hydrothermal vents. Possibly the chemistry needed for life. NASA's Europa Clipper spacecraft launched in October 2024 and is currently en route to Jupiter, arriving in 2030. It will perform nearly 50 close flybys of the moon, measuring the ice, the ocean, the magnetic field, looking for plumes. ESA's JUICE mission, also heading to the Jovian system, will visit Europa twice. Ganymede. The largest moon in the solar system, larger than the planet Mercury. Ganymede also has a subsurface ocean, confirmed by Galileo's magnetic measurements and reinforced by Hubble Space Telescope observations in 2015, which watched how the moon's auroras rocked back and forth in Jupiter's magnetic field. The rocking was less than expected, dampened, consistent with a conducting layer underground. The ocean beneath Ganymede is likely sandwiched between layers of high-pressure ice above and below, not in contact with the rocky core in the way Europa's is. This has implications for chemistry. Without direct rock-water contact, certain chemical reactions that might fuel biology become less likely. Still, an ocean. On a moon that has been in the dark, far from the sun, for 4.5 billion years. Callisto. The outermost of Jupiter's 4 large Galilean moons, heavily cratered, ancient-looking. But Galileo's magnetometer data suggested it too has a salty conducting layer beneath its surface, likely a liquid ocean, though the evidence here is less sharp than for Europa or Ganymede. The case is plausible, not certain. Enceladus. This small moon of Saturn, about 500 kilometers across, changed what planetary scientists thought was possible. In 2005, the Cassini spacecraft detected something remarkable: plumes erupting from fractures near Enceladus's south pole. Water vapor, ice particles, salt, organic molecules, spraying directly into space. These tiger stripe fractures, 4 roughly parallel cracks, each about 130 kilometers long, are the outlet for something enormous underneath. Cassini flew through the plumes multiple times. It detected hydrogen, silica particles, and complex organic compounds. In 2023, a reanalysis of Cassini's archival data, specifically from ice grains sampled in Saturn's E-ring, which is fed by Enceladus's plume, confirmed the presence of phosphorus, the last of the 6 elements considered essential for life, and the first time it had been detected in an ocean beyond Earth. All of this points to a hydrothermal system, hot water reacting with rock on the seafloor of a global ocean under the ice, the reaction products rising and eventually venting into space. Enceladus is geologically tiny and should have frozen solid long ago. It has not because of tidal heating, the same gravitational squeeze that warms Europa. What Enceladus gives scientists that Europa cannot yet provide is direct access to ocean material. The plumes go to space. A spacecraft can fly through them. The subsurface ocean on Enceladus is now considered one of the best supported cases for a potentially habitable environment in the solar system. Titan, Saturn's largest moon is unlike anything else. It has a thick nitrogen atmosphere, lakes and rivers and rain, but made of liquid methane, not water. At minus 179 degrees Celsius, water on the surface would be as rigid as granite. But beneath the surface, the picture may be different. Cassini's gravity and radio measurements hinted at a liquid layer between the icy crust and the rocky interior. Probably a water-ammonia mix. Ammonia acts as an antifreeze, lowering the freezing point. It would not be warm. It would not be the kind of water you could drink. But it would be liquid. NASA's Dragonfly mission, a nuclear-powered rotorcraft lander, is scheduled to launch in July 2028 and reach Titan in 2034. It will explore the surface and the chemistry. Titan's organic-rich environment makes it one of the most interesting places in the solar system for questions about how life's chemistry might get started. Mimas. The smallest confirmation came as a surprise. Mimas looks like the Death Star, a small, heavily cratered moon of Saturn with a massive impact crater. Nothing about it suggested internal activity. Then, in 2024, a careful reanalysis of Cassini data revealed an unexpected rocking in Mimas's orbit, a libration pattern that could only be explained by a global subsurface ocean or a highly elongated rocky core. The ocean explanation fit better. The ocean, if real, formed only 5 to 15 million years ago, geologically very recent. A young ocean on a seemingly dead moon. This finding broadened the picture considerably. Even small, ancient-looking moons might be hiding liquid water. Triton, Neptune's largest moon. Cold, geologically active, with nitrogen geysers erupting from its south polar cap. Triton orbits Neptune backwards. It is a captured object, probably a Kuiper belt body that got pulled into orbit long ago. Some models suggest that the tidal heating from its eccentric capture orbit could have sustained a subsurface ocean, though this is more speculative than the Jupiter and Saturn cases. No mission has visited Neptune since Voyager 2 flew by in 1989. Pluto and the outer reaches. In 2015, New Horizons flew past Pluto and found a world far more complex than expected. A heart-shaped nitrogen ice plain, mountains of water ice, evidence of past geological activity. Some researchers have proposed that Pluto may have had a liquid water ocean when it was young, heated by the decay of radioactive elements in its core. Whether any liquid persists today is unknown. Beyond Pluto, in the Kuiper belt, water ice is essentially a surface material, present in comets, in Kuiper belt objects like Arrokoth, detected in the debris disk around distant stars by the James Webb Space Telescope. Water is not a specialty of the inner solar system. It is the molecule that keeps showing up everywhere the temperatures are cold enough and the chemistry is right. The asteroid belt, Ceres. The dwarf planet Ceres, the largest object in the asteroid belt, about 945 kilometers across, was not expected to have water activity. But in 2014, the Herschel Space Observatory detected water vapor rising from 2 regions on its surface. Then NASA's Dawn spacecraft arrived in 2015 and found bright spots inside Akator crater, sodium carbonate deposits left behind by briny water that seeped up to the surface and evaporated. Ceres has a mountain called Ahuna Mons, a cryovolcanic dome thought to have been pushed up by slushy water-salt material from below. Ice is present in permanently shadowed craters at its poles. The picture that emerged is of a world with ongoing low-level cryovolcanic activity, water quietly moving through its interior even today. What the pattern tells us. Step back and look at the full inventory. Water ice is confirmed on the Moon, Mars, Ceres, Europa, Ganymede, Callisto, Enceladus, Mimas, Titan, and in comets throughout the solar system. Subsurface liquid water is strongly supported for Europa and Enceladus, and plausibly for Ganymede, Callisto, Titan, and Mimas. Mars may have liquid water deep underground. Triton and Pluto are possible candidates. The solar system, which once seemed to be a collection of dry rocks and gas orbiting a star, turns out to be saturated with water, mostly frozen, occasionally liquid, almost everywhere below the surface of any body large enough to hold heat. Earth is not exceptional for having water. It is exceptional for having water on its surface, under pressure from a thick atmosphere, at exactly the temperature range that keeps it liquid. That specific combination, not the water itself, is what makes Earth unusual. Everywhere else, the water hides. But it is there. What happens next depends on the missions being built and launched right now. Europa Clipper is already en route. JUICE is heading to Jupiter. Dragonfly will reach Titan in 2034. Each of those missions will carry instruments capable of characterizing subsurface oceans in more detail than has ever been possible from Earth. The question the scientists keep asking is not whether water exists beyond Earth. That question has been answered, repeatedly, in location after location. The question now is what that water contains, what chemistry, what molecules, what signatures, if any, of something more. That answer is still coming. If you found this useful, subscribe and let us know in the comments which